Tonight, we're going to explore something that might sound like science fiction, but is actually happening in physics labs right now. For decades, physicists have been wrestling with a seemingly impossible problem. How do you cross the vast distances between stars when the laws of physics say you can't? The nearest star is so far away that even spacecraft like Voyager would take 70,000 years to reach it. And Einstein's equations seem to forbid any shortcut. But in 2024, a small research team published a paper that changed the conversation entirely. They found a solution hiding in the mathematics. A way to move through space that doesn't break the speed of light, but doesn't need to. By the end of tonight, you're going to see exactly what they discovered in those equations, and why physics just opened a door everyone thought was permanently sealed. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The nearest star beyond our Sun sits 25 trillion miles away. That's 25 with 12 zeros after it. This is the distance to Proxima Centauri, a small red dwarf star that happens to be our closest stellar neighbor in the entire galaxy. It's sitting out there in the constellation Centaurus, visible from the southern hemisphere, burning quietly at a fraction of our Sun's brightness. And it's closer to us than any other star in the night sky. 25 trillion miles might not mean much intuitively, because our brains didn't evolve to handle numbers that large. So let me put it in context. Light, the fastest thing in the known universe, travels at roughly 186,000 miles per second, or 300,000 kilometers per second. At that speed, light could circle Earth's equator more than 7 times in 1 second. In the time it takes you to snap your fingers, a photon could race from New York to Tokyo and back again. Nothing in nature moves faster than light. Not particles, not energy, not information. The speed of light is the universe's ultimate speed limit, built into the fabric of reality itself by the laws of physics. And even at that incomprehensible velocity, it takes light 4 years and 3 months to travel from our Sun to Proxima Centauri. Think about that. A beam of light leaving Proxima Centauri today, right now, this instant, won't arrive at Earth until sometime in the year 2030, more than 4 years from now. That's the scale of the problem. Now, let's talk about our actual capability to cross that distance. One of our most distant spacecraft is Voyager 1, launched on September 5th, 1977, from Cape Canaveral, Florida. Voyager 1 has been traveling through space for almost 50 years. It's currently farther from Earth than any other human-made object. In August 2012, Voyager 1 crossed the heliopause, the boundary where the Sun's solar wind gives way to the interstellar medium. It became the first human-made object to enter interstellar space. It's still out there, still operational, still sending back data across billions of miles of empty space. And it's moving fast. Voyager 1 is currently traveling at approximately 38,000 miles per hour relative to our Sun. That sounds incredibly fast. It is fast by every measure we use in daily life. A commercial airliner cruises at about 600 miles per hour. The fastest car ever built, the Thrust SSC, hit a top speed of about 760 miles per hour. A bullet, fired from a high-powered rifle, leaves the barrel at around 2,000 miles per hour. Voyager 1 is moving 19 times faster than a speeding bullet. It's covering roughly 333 million miles every year. That's fast enough to travel from Earth to the Moon in less than 7 hours. Fast enough to reach Mars in a matter of weeks during a close approach. But now, plug that velocity into the equation for reaching Proxima Centauri. The math is simple and devastating. At 38,000 miles per hour, traveling 25 trillion miles takes approximately 70,000 years. 70,000 years. Let that sink in for a moment. When Voyager 1 finally approaches Proxima Centauri 70,000 years from now, if it were actually heading in that direction, humanity, as we know it today, will likely be unrecognizable. And Proxima Centauri is the nearest star. If you wanted to visit Sirius, the brightest star in our night sky, the journey would take about 150,000 years at Voyager's speed. Sirius sits 8.6 light-years away. Betelgeuse, the red supergiant marking the shoulder of Orion, is about 550 light-years distant. A Voyager-class probe, heading there, wouldn't arrive before our sun exhausted its hydrogen fuel and began swelling into a red giant, consuming the inner planets, including Earth. The engineering reality is brutal. You cannot inch your way to the stars by building slightly faster chemical rockets. The problem isn't that our engines aren't powerful enough. The problem is physics itself. Every rocket ever designed works on the same principle. You carry fuel, you burn it, and the exhaust provides thrust. But fuel has mass, and that mass needs to be accelerated along with the spacecraft, which means you need more fuel to push the fuel, which adds more mass, which requires even more fuel to accelerate. The relationship is exponential, not linear. It's called the tyranny of the rocket equation, and it's been the bane of space exploration since the beginning. The Saturn V rocket that carried astronauts to the moon during the Apollo program burned through 3,000 tons of fuel in its first stage alone. 3 million kilograms of kerosene and liquid oxygen consumed in just 2.5 minutes. All of that fuel, all of that mass, all of that expense to push a tiny capsule containing 3 human beings 250,000 miles to the moon. Now scale that up. Proxima Centauri is 100 million times farther away than the moon. If you tried to use chemical rockets to reach Proxima in a human lifetime, you would need more fuel than exists on Earth. Not an exaggeration. The actual calculation says you'd need more hydrocarbons than you could extract from every oil deposit, every natural gas reserve, every organic compound on the planet. And that still wouldn't be enough. You'd need to harvest hydrocarbons from the atmospheres of Jupiter and Saturn. You'd need to strip every organic molecule from every asteroid and comet in the solar system. And even then, the numbers don't work. The rocket equation doesn't care how much fuel you have. It cares about the ratio between fuel mass and payload mass. And for interstellar travel with chemical propulsion, that ratio explodes to impossible values. Engineers have known this since the 1950s, which is why every serious proposal for interstellar travel has tried to sidestep chemical engines entirely. Nuclear pulse propulsion was one early idea. The concept, developed in the 1950s and 60s under Project Orion, involved detonating nuclear bombs behind a massive spacecraft and riding the shockwave. Each explosion would push against a huge steel plate connected to the ship by shock absorbers, accelerating the vehicle forward. It's a brute force approach that sounds insane and probably is. But the physics works. Nuclear explosions release far more energy per unit mass than any chemical reaction. In theory, a ship powered by nuclear pulse propulsion could reach a few percent of the speed of light. At 3% of light speed, Proxima Centauri becomes a 140-year voyage instead of 70,000. Still longer than a human lifetime, but at least within the realm of generational ships. The practical problems are enormous. You'd need thousands of nuclear warheads. The radiation shielding would have to be massive. The political and environmental concerns of launching such a ship from Earth are probably insurmountable, and it's never been built. Fusion propulsion is another approach. Instead of fission, you'd burn hydrogen fuel the way stars do, fusing light elements into heavier ones and extracting the energy released. Fusion engines would be more efficient than chemical rockets and cleaner than fission. But we haven't mastered controlled fusion yet, even for stationary power plants. Building a fusion rocket that works in the hostile environment of space is still decades away, at minimum. Antimatter propulsion represents the theoretical maximum efficiency. When matter and antimatter collide, they annihilate completely, converting 100% of their mass into energy. According to Einstein's famous equation, E equals mc squared. Nothing releases more energy per unit mass than matter-antimatter annihilation. An antimatter engine could theoretically accelerate a spacecraft to a significant fraction of light speed. The problems are that antimatter doesn't exist naturally in useful quantities. Every atom of antimatter has to be manufactured in particle accelerators at enormous energy cost. Current production rates are measured in billionths of a gram per year. Building up enough antimatter fuel for an interstellar mission would take longer than the mission itself. And storing antimatter without it touching ordinary matter and exploding is an unsolved engineering challenge. Solar sails represent a completely different approach. Instead of carrying fuel, a solar sail uses pressure from sunlight or powerful lasers to accelerate. Light carries momentum, and a large reflective sail can be pushed by photons, the way a sailboat is pushed by wind. The Breakthrough Starshot initiative, funded by Yuri Milner and supported by scientists, including Stephen Hawking before his death, proposed using ground-based laser arrays to push tiny spacecraft equipped with light sails. The concept calls for accelerating gram-scale probes to 20% of light speed. At that velocity, they could reach Proxima Centauri in about 20 years and send back data via laser communication. It's an ambitious project, and it might work for tiny unmanned probes, but it doesn't scale to crewed missions. A light sail large enough to push a spacecraft containing humans would need to be hundreds of miles across. And the laser array powerful enough to accelerate it would require energy output comparable to a significant fraction of all power generation on Earth. Every one of these approaches claws a little closer to practical interstellar capability. Each one represents genuine progress in propulsion physics. But none of them cracks the real ceiling. The real ceiling is the speed of light, roughly 186,000 miles per second, or 300,000 kilometers per second. This isn't just the speed limit we haven't broken yet, with better engineering. It's a fundamental law of nature, woven into the structure of spacetime itself. In 1905, Albert Einstein published his theory of special relativity. Among other things, it proved that nothing with mass can be accelerated to the speed of light. The reason is that as an object approaches light speed, its effective mass increases. The closer you get to that ultimate velocity, the more energy you need to gain the next mile per hour. At 99% of light speed, the ship's apparent mass has grown by a factor of 7. At 99.9%, by a factor of 22. To actually reach light speed would require infinite energy. Infinite energy doesn't exist. Therefore, nothing with mass can reach the speed of light. This isn't a technological limitation. It's not a problem we can solve with better rockets or more advanced materials. It's built into the geometry of the universe. The speed of light is more than just a speed. It's the speed at which causality propagates. The maximum rate at which information can travel from one point to another. The cosmic speed limit is absolute. Or so everyone thought, until a young physicist in Wales asked a different kind of question. In 1994, Miguel Alcubierre was a 28-year-old theoretical physicist working at the University of Wales in Cardiff. Trained at the National Autonomous University of Mexico, pursuing postdoctoral work in Europe, and he was a fan of Star Trek. Star Trek, for those unfamiliar, is a science fiction television series that first aired in the 1960s. The show's starships travel faster than light using something called warp drive. The characters talk about traveling at warp 2, warp 5, warp 9, speeds that let them cross interstellar distances in days or hours instead of decades. The show never explained how warp drive works. It was science fiction, not science fact. Most physicists dismissed it as fantasy because Einstein's equations said faster-than-light travel was impossible. Alcubierre decided to treat it as a homework problem. He sat down with Einstein's field equations, the mathematical foundation of general relativity, the theory that describes how gravity works by curving spacetime. And he asked those equations a very specific question. What shape would spacetime need to have for a region inside it to move faster than light, without any object within that region actually exceeding light speed? At first glance, this sounds like cheating. Like asking how to go faster than light without going faster than light. But Alcubierre realized there's a loophole in Einstein's equations that nobody had seriously explored. Einstein's speed limit applies to objects moving through space. It doesn't say anything about space itself moving. And there's a big difference. Let me explain. When we say nothing can move faster than light, we mean nothing can move through spacetime faster than light. A rocket accelerating, a particle in a collider, a radio signal, all of these are objects or waves propagating through the fabric of spacetime. Einstein's equations firmly prohibit them from exceeding light speed. But Einstein's equations also describe how spacetime itself can change shape. How it can curve, stretch, compress, even expand. And there's no speed limit on that. We know space itself can move faster than light because we see it happening. The universe is expanding. Distant galaxies are receding from us, and the farther away they are, the faster they're moving. At a certain distance, roughly 14 billion light-years from Earth, galaxies are receding faster than light itself. Not because the galaxies are moving through space at superluminal velocities, but because the space between us and them is stretching. The galaxies are like ants on a rubber sheet. If you pull the sheet, the ants separate. Not because they're walking away from each other, but because the sheet itself is getting bigger. The ants are riding the expansion, and there's no limit to how fast the sheet can stretch. This is called metric expansion, and it's been observationally confirmed by decades of astronomical measurements. Alcubierre looked at this loophole and asked the obvious question. If space can carry galaxies apart at faster than light velocities, could it carry a spacecraft? Could you engineer a local region of spacetime to compress in front of a ship, expand behind it, and let the ship ride the resulting wave? He worked through the mathematics carefully. General relativity describes spacetime using something called a metric, which is essentially a mathematical recipe for calculating distances and times. Different metrics describe different shapes of spacetime. The metric for flat, empty space is called the Minkowski metric. The metric around a massive object like a star is called the Schwarzschild metric. which describes how gravity curves spacetime. The metric around a rotating black hole is the Kerr metric. Each metric is a solution to Einstein's field equations. Alcubierre constructed a new metric, a metric that describes a bubble. Inside the bubble, the metric is flat. Space behaves normally. Time ticks at standard rates. Light moves at standard speed. An astronaut inside would feel nothing unusual. No gravity, no forces, no acceleration. Outside the bubble, the metric is also flat, matching the rest of the universe. But at the boundary of the bubble, the metric does something remarkable. On the leading edge, space contracts sharply. The metric components change in a way that compresses distances in front of the bubble. On the trailing edge, space expands just as sharply. Distances stretch out behind the bubble. The bubble itself rides forward on this geometry. From an outside observer's perspective, the bubble translates through space at any speed whatsoever. Faster than light, slower than light, whatever you choose. But from the perspective of someone inside the bubble, nothing is moving at all. The ship sits in a pocket of flat space-time. That pocket shifts position because the universe around it is reconfiguring. The ship doesn't accelerate. It doesn't experience relativistic effects. It doesn't gain kinetic energy in the traditional sense. It's surfing a wave in the geometry of space-time itself. Alcubierre published his result in May 1994 in the journal Classical and Quantum Gravity. The title was The Warp Drive, Hyper-Fast Travel Within General Relativity. It was 8 pages long, dense with tensor mathematics and diagrams showing how the metric components behaved. And it became one of the most cited papers in theoretical physics of that decade. When it appeared, the physics community reacted with a mixture of excitement and skepticism. The excitement came from the fact that the math was correct. Alcubierre's metric was a valid solution to Einstein's field equations. It wasn't a trick or a mistake. It genuinely described a space-time geometry where a bubble could move faster than light without violating relativity locally. Einstein's speed limit still held. Inside the bubble, light always moved at light speed. Outside the bubble, the same. Nothing was traveling through space faster than light. But the bubble as a whole could cross interstellar distances faster than any light beam following the normal path. The skepticism came from what the solution required to actually build. Alcubierre's warp bubble needed something that nobody had ever seen. It needed exotic matter. Specifically, it needed matter with negative energy density. Let me explain what that means. Ordinary matter, the kind everything around you is made of, has positive energy. A rock has positive energy. A gas cloud in space has positive energy. Even the vacuum of space, thanks to quantum fluctuations, has a small positive energy density. Positive energy curves, space-time inward. That's what we call gravity. Mass pulls other mass toward it. Negative energy would do the opposite. It would curve space-time outward, creating a repulsive effect. Anti-gravity. Nothing in the everyday world behaves this way. You've never seen an object that falls upward. You've never encountered a substance that pushes other things away gravitationally. Negative energy, if it exists at all, is not part of the normal material inventory of the universe. And Alcubierre's warp bubble required vast amounts of it. The negative energy would need to be arranged in a shell around the spacecraft, filling the boundary region where space-time transitions from contracted in front to expanded behind. That shell of exotic matter is what holds the bubble together. Without it, the geometry collapses. The early calculations for how much negative energy you'd need were absolutely catastrophic. Physicists who worked through the numbers came back with estimates saying you'd need exotic matter equivalent to the mass of the entire observable universe. Every star, every galaxy, every planet, every particle of dust in every direction, out to the cosmic horizon. All of it converted into negative energy and concentrated into a shell around your spacecraft. The number was so absurd that many researchers assumed they'd made an error. They hadn't. The original Alcubierre metric was what theorists call energy inefficient. The way the bubble was shaped, with a very thin and sharply curved transition region, drove the energy requirements into impossible territory. Later, papers brought the number down, but not by enough to make anyone optimistic. The metric remained a beautiful piece of mathematics with no clear connection to engineering reality. And for the next decade, that's mostly how the physics community treated it. An interesting solution to Einstein's equations. A proof that faster-than-light travel wasn't strictly forbidden by the mathematics of general relativity, but not something anyone expected to actually build. Then, in 1999, a physicist in Belgium found a way to dramatically reduce the exotic matter requirement. Chris van den Broek was working at the Free University of Brussels when he published a paper that changed the conversation about warp drive. The paper appeared in Classical and Quantum Gravity, the same journal that had published Alcubierre's original work. Van den Broek's insight was subtle but powerful. He realized that the external size of the warp bubble and the internal size don't have to match. In flat, ordinary space, they obviously do. A box that looks 1 meter wide on the outside contains 1 meter of space on the inside. But in curved space-time, that relationship can break. General relativity allows geometries where a small exterior volume contains a large interior space. The classic example is a wormhole, where you could theoretically have a mouth the size of a door that opens into a tunnel stretching thousands of light years. The exterior size and the interior size are decoupled by the curvature. Van den Broek applied this idea to the warp bubble. He proposed shrinking the bubble's exterior to absurdly small dimensions, on the order of 10 to the negative 15th meters. That's about the size of an atomic nucleus. A proton is roughly 1 femtometer across. Van den Broek's warp bubble would have an outer radius comparable to that. From the outside, looking at it with any instrument, the bubble would be microscopic, smaller than any atom, invisible to all but the most exotic particle detectors. But inside, thanks to the curved geometry, there would be a normal-sized region of flat space. Plenty of room for a spacecraft and crew. It sounds impossible. How can a spacecraft fit inside something smaller than an atom? The answer is that general relativity allows the interior volume to be larger than the exterior suggests. The curvature of space-time handles the mismatch. Think of it like those fictional bags in fantasy stories that are bigger on the inside than the outside. In general relativity, that's not magic. It's geometry. By making this change, Van den Broek reduced the exotic matter requirement by more than 20 orders of magnitude. The number dropped from something like the mass of the observable universe down to something closer to the mass of Jupiter. Jupiter has a mass of about 2 times 10 to the 27th kilograms. 2 trillion kilograms. Still enormous. Still far beyond anything we could collect or manipulate. But a reduction by a factor of 100 billion is not nothing. It meant the problem had moved. The warp drive went from requiring literally all the matter in the universe to requiring the mass of one large planet. From absolutely impossible to merely ridiculously impossible. Van den Broek's design also satisfied certain quantum energy conditions that the original Alcubierre metric violated. The weak energy condition, one of several mathematical criteria that rule out the most pathological kinds of negative energy, was met by Van den Broek's geometry. That was significant because it suggested the design might be more physically reasonable than Alcubierre's original. The trade-off was that Van den Broek's bubble required spacetime curvature to remain well-behaved at atomic length scales, and general relativity has never been tested there. At the scale of a proton, quantum effects dominate. Nobody knows for certain whether spacetime behaves classically the way Einstein's equations describe. It might not. The experiment hasn't been done because nobody knows how to do it. The physics community treated Van den Broek's paper as progress. Real progress. It proved that the exotic matter requirement wasn't locked to the universe scale. Numbers of the original design. The requirement could move, sometimes dramatically, with clever geometric choices. That meant other optimizations might be possible. Other researchers began exploring variations. A physicist named Jose Notario proposed a warp bubble with no space contraction or expansion at all, just a tangential flow of spacetime around the ship, like water flowing around a rock in a river. Notario's design avoided some of the original problems, but introduced new ones. The field was starting to mature. By the early 2000s, warp drive theory had become a small but active research area. Papers appeared every year or two, each one shaving a little more off the energy budget or fixing a different technical flaw. The numbers were still impossible, but the trajectory was downward, and the engineering picture was becoming clearer. Then, in 2011, a NASA physicist walked into the conversation with a redesign that shocked even the specialists. Harold White worked at NASA's Johnson Space Center in Houston, Texas. Not in the public relations department or mission planning. White was part of an internal research division called EagleWorks, the Advanced Propulsion Physics Laboratory. EagleWorks was NASA's home for speculative physics, the place where engineers could explore ideas that sounded like science fiction but had roots in actual mathematics. Concepts like warp drive, wormholes, and other exotic propulsion schemes that might, in some distant future, become relevant to actual mission design. White had been studying Alcubierre's work for years. He understood the mathematics deeply. He knew the energy requirements were absurd. But he also knew that the requirements depended heavily on the specific shape of the warp bubble, and he thought there might be room for optimization that previous researchers had missed. In September 2011, White presented a new warp drive design at the 100-Year Starship Symposium in Orlando, Florida. The symposium was a gathering of scientists, engineers, futurists, and enthusiasts interested in long-term space exploration. The audience included physicists from major universities, NASA engineers, private space company representatives, and a handful of science journalists. White's presentation made headlines. What he showed was a geometric redesign of the Alcubierre warp bubble that reduced the exotic matter requirement by another enormous factor. White didn't question whether warp drive was theoretically valid. He took that as given. What he presented was an engineering optimization. The key change involved the thickness of the bubble wall. In Alcubierre's original design, and in most subsequent variations, the transition region, where space shifts from contracted to expanded, was thin, very thin. The metric changed sharply over a small distance. That sharpness, that steep gradient in the geometry, was part of what drove the energy cost so high. White proposed widening the transition zone. Instead of a thin shell, his bubble had a thick, gradual boundary. The compressed region in front and the expanded region behind would still do their work. But the change would happen over a larger volume. The gradient would be softer, less extreme. He also changed the cross-sectional shape of the bubble. Instead of a sphere, White's bubble was shaped like a torus, a donut. The spacecraft would ride through the hole in the middle. The torus geometry concentrated the spacetime warping in specific regions and left other areas relatively flat. This reduced the integrated energy cost across the entire structure. When White ran the numbers using this thicker wall torus geometry, the exotic matter requirement dropped to about 700 kilograms. 700 kilograms, the mass of a large motorcycle, roughly 1,500 pounds. Compared to the mass of Jupiter or the observable universe, this was almost trivial. If exotic matter existed in pure concentrated form, 700 kilograms would fit in a medium-sized room. It was still impossible because nobody had ever produced a single gram of exotic matter. But it was impossible on a completely different scale. The problem had gone from requiring an impossible amount of an impossible substance to requiring a merely very difficult amount of an impossible substance. White went further. He proposed that Eagleworks could actually test whether small amounts of space-time warping could be created in a laboratory. The experimental setup would use a device called a White-Jude warp field interferometer. The concept was similar, in principle, to the Michelson-Morley interferometer, the instrument that helped establish special relativity by showing that the speed of light is constant in all directions, and similar to the instruments that decades later would detect gravitational waves at LIGO. An interferometer works by splitting a laser beam into two paths, bouncing the beams off mirrors and recombining them. If one path is even slightly longer or shorter than the other, the beams will interfere when they recombine, creating a pattern of light and dark fringes. By measuring that interference pattern with extraordinary precision, you can detect tiny changes in the length of the paths. Changes far smaller than the width of an atom. White's idea was to look for microscale spacetime warping around a specially designed apparatus. The apparatus would consist of high-voltage capacitor rings arranged in a specific geometry. If the warp field theory was correct, and if it scaled down to small sizes, the electric fields around those capacitors might produce a tiny local curvature of spacetime. Not enough to move anything, but potentially enough to shift the interference pattern in the laser by a measurable amount. Eagleworks built the interferometer. They ran the experiment. The results were ambiguous. White's team reported detecting anomalous shifts in the interference pattern under certain conditions. But the shifts were small, barely above the noise threshold, and there were multiple possible explanations that had nothing to do with spacetime curvature. Thermal expansion of the optical components, air currents in the laboratory, electromagnetic interference from the high-voltage capacitors, vibrations from nearby equipment. All of these could produce similar interference patterns. The experimental controls weren't tight enough to rule them out definitively. Critics in the physics community pointed out that extraordinary claims require extraordinary evidence, and detecting spacetime curvature in a tabletop experiment would be an extraordinary claim. The evidence White presented wasn't extraordinary. It was suggestive at best. NASA never officially claimed that warp field effects had been detected. The agency was careful to describe the results as preliminary and requiring further investigation. But the fact that NASA was funding this work at all was significant. The largest and most respected space agency on Earth was taking warp drive seriously enough to allocate resources, build hardware, and publish results. That gave the field a legitimacy it had never had before. Graduate students could study warp metrics without their advisors questioning their career choices. Papers on warp drive started appearing in mainstream physics journals, not just fringe publications. Conferences began including sessions on advanced propulsion concepts. The energy budget for building a warp bubble had dropped from universe scale to planet scale to motorcycle scale. The bubble had been reshaped, optimized, and refined through multiple iterations. And yet, the fundamental problem remained. 700 kilograms of exotic matter is still 700 kilograms of something nobody had ever produced. Something that might not exist at all in the form required, which is where a small, privately funded research lab in New York enters the story with an entirely different approach. 477 Madison Avenue, Midtown Manhattan, New York City. An office building among thousands in one of the densest urban environments on Earth. Inside that building, on one of the upper floors, sits the headquarters of a research organization called Applied Physics. Applied Physics is not a university. It's not a government lab. It's a private entity funded by investors interested in breakthrough physics and advanced technology. The organization was founded by Gianni Martire, an engineer and entrepreneur who had worked in aerospace and technology sectors before deciding to focus on fundamental physics research. The company operates a division called the Advanced Propulsion Laboratory. The mission is simple: treat warp drive not as a theoretical curiosity, but as an engineering problem that can be systematically solved. Map the solution space. Identify the requirements. Develop the tools to evaluate candidate designs. And eventually, build hardware. The team is small, under a dozen core researchers. But the researchers are serious. They hold PhDs from respected institutions. They publish in peer-reviewed journals. They attend conferences and present their work alongside academic physicists. The scientific staff includes Alexei Bobrik, a theoretical physicist, Jared Fuchs, trained at the University of Alabama in Huntsville, Christopher Helmerich, also from Alabama, Luke Sellers, Brandon Melchior, and several affiliated researchers at partner institutions. Unlike NASA's Eagle Works, which had to justify its research to government oversight and public scrutiny, Applied Physics could pursue long-term speculative projects without political pressure. If the work didn't produce results for a decade, that was fine. The investors understood they were funding basic research with uncertain timelines. In February 2021, two members of the Applied Physics team, Alexei Bobrik and Gianni Martire, published a landmark paper. The title was Introducing Physical Warp Drives. The paper appeared in Classical and Quantum Gravity, the same journal that had published Alcubierre's original work and most of the subsequent refinements. What Bobrik and Martire did was different from previous papers. They didn't propose a specific new warp drive design. Instead, they created a general framework for classifying all possible warp drive spacetimes, a taxonomy, a way of organizing the entire solution space. The core insight was elegant. Every warp drive, without exception, consists of three regions. First, an asymptotically flat region far from the ship. This is ordinary space, the kind we live in, flat, or nearly so, matching the vacuum of the universe far from any massive objects. Second, a passenger region at the center. This is also flat. It's where the crew lives, where the ship's hull and equipment sit, where clocks tick normally and the laws of physics behave as expected. Third, a warping region in between. This is the shell of curved spacetime that does all the work. The region where the metric transitions from flat interior to flat exterior, creating the compression ahead and expansion behind. Every warp drive ever proposed, from Alcubierre's original to Van den Broek's shrunken bubble to White's torus, fits into this three-region framework. The differences between designs come down to how the warping region is shaped. What kind of matter or energy fills it? How thick it is? How sharply curved it is? And how the bubble interfaces with the surrounding universe. By mapping all warp drives into this common structure, Bobrick and Martyr could ask systematic questions. Which regions of the design space had been explored? Which hadn't? What constraints applied universally? What features were optional? They found large territories that no previous paper had investigated. One of those territories was the subluminal warp drive. Most research for the previous 30 years had focused on superluminal designs, faster than light, because that was the whole point. If you're going to violate causality and bend the rules of space-time, you might as well go all the way and beat the ultimate speed limit. Bobrick and Martyr pointed out that subluminal warp drives, bubbles moving slower than light, might be much easier to build. They might satisfy energy conditions that exotic matter violates. They might not require negative energy at all. And they would still be incredibly useful. A warp bubble traveling at 90% of light speed doesn't break Einstein's cosmic speed limit, but it would cross the solar system in hours, reach Proxima Centauri in under 5 years, and do so without subjecting the crew to any acceleration forces whatsoever. The paper also proved a theorem that hadn't been stated explicitly before. Any warp drive, regardless of its design, is effectively a shell of matter that has been set in motion. The shell moves through space like any other object, which means it still needs some kind of propulsion system to accelerate it to cruising speed. A warp bubble doesn't eliminate the need for rockets. It changes what the rocket is pushing. Instead of pushing the spacecraft directly, accelerating the crew and cargo, the rocket accelerates the bubble. And the bubble carries everything inside it without transmitting any forces to the interior. This reframed the entire problem. Warp drive wasn't magic. It was a specific kind of structured space-time geometry that, once set in motion, carried a region of flat space along with it. The internal crew felt no G-forces because they weren't accelerating. The external universe saw the bubble move. But getting the bubble up to speed in the first place still required conventional physics. The Bobrick-Martyr framework became the standard reference for warp drive research going forward. Papers published after 2021 cite it heavily. The classification scheme is now used to describe new designs. And the focus on subluminal configurations opened a research direction that had been largely ignored. The applied physics team continued working. They had classified the problem. Now they needed to solve it. In 2024, they did. Classical and Quantum Gravity, Volume 41, Number 9. Article 0, 95013. Published April 29th, 2024. The title: Constant Velocity Physical Warp Drive Solution. Lead author: Jared Fuchs. Co-authors: Christopher Helmerich, Alexei Bobrik, Luke Sellers, Gianni Martire. The entire applied physics team, pulling together, focused on a single problem. What the paper claimed was extraordinary. The authors presented a warp drive solution that satisfies all of the classical energy conditions. All of them. The weak energy condition, the null energy condition, the dominant energy condition, the strong energy condition. These are mathematical criteria that ordinary matter satisfies and that exotic matter violates. They're not arbitrary rules. They emerge from quantum field theory and have been tested against countless observations. Violating them usually means you're dealing with something unphysical, something that doesn't exist in nature. The Fuchs warp drive violates none of them. No negative energy anywhere in the structure. No exotic matter. No violations of any physical principle observed in the real universe. The design combines two elements. First, a stable matter shell with a specific density distribution, built entirely from positive energy material. The kind of matter that exists throughout the universe. Ordinary baryonic matter. Protons, neutrons, electrons, arranged in specific configurations. Nothing exotic. Nothing that requires new physics to produce. Second, a shift vector distribution. This is a mathematical feature of the spacetime metric. It describes how different parts of space are moving relative to each other. In the Fuchs design, the shift vector creates a flow pattern that mimics the Alcubierre geometry. Space compresses slightly ahead of the bubble, expands slightly behind it. But the compression and expansion are driven by the distribution of ordinary matter in the shell, interacting with the shift vector structure. Together, the shell and the shift vector produce a warp effect. A region of flat space moves through the surrounding universe, carrying anything inside it along for the ride. The paper uses software called Warp Factory to evaluate the design numerically. Warp Factory is a tool the applied physics team developed and released publicly. Written in MATLAB, it allows researchers to input any proposed warp metric and calculate its properties. The stress-energy tensor, which tells you what kind of matter would be needed. The energy conditions, which tell you whether that matter is physical. The curvature scalars, which describe how strongly spacetime is bending. And visualizations that let you see the geometry. When you run the Fuchs metric through Warp Factory, the output is clean. The visualization shows blue everywhere. Blue indicates positive energy density, the kind that matches ordinary matter. Black lines show momentum flux, the internal structure of how energy and momentum flow through the bubble. Nowhere in the entire visualization does red appear. Red would indicate a violation of the energy conditions, a region requiring exotic matter. The Fuchs warp drive has no red. It's entirely blue, entirely physical, entirely consistent with known physics. Fuchs explained the breakthrough in interviews and press releases. Prior warp drive models, he said, required matter and energy content that was unphysical. Features nobody has ever observed in nature. The new approach avoided that by adding positive energy to the solution while keeping as much of the warp effect as possible. When physicists talk about positive energy, they mean phenomena like light, ordinary matter, and antimatter, all of which exist naturally, all of which we can detect, measure, and in some cases produce. The solution also uses gravity itself as part of the warping mechanism. Gravity is already a manifestation of curved spacetime, a sufficiently dense and precisely shaped distribution of ordinary matter curves space around it. That curvature, when combined with the shift vector structure, produces the warp bubble. No exotic physics required. For the first time since Miguel Alcubierre's original paper 30 years earlier, a warp drive design existed that didn't require anything the universe refuses to provide. The physics community reacted with cautious optimism. Mainstream physicists acknowledged that the solution was mathematically valid. It satisfied the energy conditions as claimed. It represented genuine progress. Skeptics pointed out that a warp drive using only positive energy, while novel, doesn't solve the interstellar travel problem if it can't go faster than light. And the Fuchs design cannot. Because the paper includes a caveat that headlines often buried. This solution is explicitly subluminal. The bubble moves at a constant velocity, and that velocity is less than the speed of light. Subluminal means below light speed. The Fuchs warp drive does not enable faster than light travel. It does not let you reach Proxima Centauri in days or weeks. It does not break Einstein's cosmic speed limit. What it does is prove that warp spacetimes, as a class of solutions, are not inherently dependent on exotic matter. At least some warp configurations can be built from ordinary positive energy materials. Using physics we already understand. Fuchs was careful about this limitation in every interview. He told reporters plainly that this concept will not deliver Star Trek-style rapid interstellar transport. What it delivers, he said, is the warp effect itself. The ability to accelerate passengers without subjecting them to G-forces, using regular matter. And that capability, even at subluminal speeds, could lead to other interesting applications. Let me explain why this matters. A subluminal warp bubble, traveling at, say, 90% of the speed of light, would take about 4.7 years to reach Proxima Centauri as measured by outside observers. For the crew, due to time dilation, the subjective experience would be shorter, roughly 2 years. That's still a long trip. It's not the weeks or months of science fiction, but it's no longer generational. It's within the career span of a single astronaut. Someone could volunteer for the mission, make the journey, and return within their working lifetime. More importantly, a subluminal warp drive transforms travel within the solar system. Right now, a trip to Mars takes about 6 to 9 months, depending on the alignment of the planets. The spacecraft has to coast most of the way, because sustained thrust would require too much fuel and would crush the crew. A Mars mission is a slow, careful ballet of orbital mechanics. Launch windows open only every 26 months. The trajectory is fixed months in advance. Mid-course corrections are limited. It's cumbersome and restrictive. A warp bubble changes everything. Inside the bubble, space is flat. The crew experiences no acceleration. Even if the bubble itself is accelerating rapidly, the passengers feel nothing. A warp ship could fire its engines continuously, accelerating to a significant fraction of light speed, coast briefly, then decelerate just as hard. The entire trip to Mars could be measured in days instead of months, possibly hours if you pushed the acceleration high enough. The crew would arrive fresh, unaffected by the brutal forces that would normally accompany such a journey. The same logic applies to everywhere else in the solar system. Jupiter, currently a multi-year voyage, becomes a matter of weeks. Saturn, Neptune, the Kuiper Belt, all within reach of short-duration missions. You could send crewed expeditions to study these worlds up close without committing decades of an astronaut's life to the journey. And there's a safety benefit most coverage overlooks. A subluminal warp bubble does not generate a horizon at its leading edge. Let me explain what that means and why it matters. When a bubble moves faster than light, the front edge is receding from the ship's interior, faster than any signal from inside could catch up. This creates what's called an event horizon, a boundary beyond which the interior cannot send information. Horizons are bad news. They produce Hawking radiation, a quantum effect that would irradiate the crew. They prevent steering because you lose causal contact with your own leading edge. They trap particles which get released as a devastating beam when the bubble shuts off. All of these problems are features of superluminal travel specifically. A subluminal bubble doesn't cross the light barrier. No horizon forms. No Hawking radiation. No loss of control. No particle beam weapon. The ship remains in causal contact with its entire structure. The pilot can steer, adjust course, and decelerate safely. The physics permits it. The materials are ordinary. The crew is protected. And for the first time, there's an actual engineering path connecting our current technology to eventual warp capability. Not a path we can walk tomorrow. Not even a path we can walk this century. But a path. The engineering challenges are still enormous. Building a matter shell with the density profile the Fuchs design requires is far beyond our current materials science. The shell would need to maintain its shape against gravitational stresses, thermal fluctuations, and the dynamic forces of acceleration and deceleration. Current high-strength materials, things like carbon fiber composites and advanced steel alloys, can handle pressures up to a few gigapascals. The warp shell would need to handle stresses thousands of times higher without deforming or failing. We don't have materials that can do that. We might not have them for centuries. The energy requirements are also staggering. Even though the Fuchs design doesn't need exotic matter, it still needs energy. Lots of it. Accelerating a massive shell of ordinary matter to 90% of light speed requires energy inputs comparable to significant fractions of global power production. We're talking terawatts, sustained over hours or days. That's energy on a scale we've never attempted. The instrumentation to test even small-scale warp effects doesn't exist yet. Before anyone builds a full-scale warp ship, someone needs to demonstrate that the effect works at laboratory scale. That means building interferometers sensitive enough to detect spacetime curvature around benchtop experiments. Current instruments can measure gravitational waves from colliding black holes billions of light-years away. But measuring static local curvature from a small matter distribution is a different problem entirely. It requires precision we haven't achieved. Nobody is building a warp drive this decade. Or next decade. Probably not this century. But the physics allows it. The math is clean. The materials are ordinary, even if we can't shape them properly yet. And there's a research community actively working on the problem. In early 2026, less than 2 years after the Fuchs paper, another study suggested the next refinement might already be on the horizon. A follow-up paper from the applied physics team and collaborators revisited the warp drive metric families with more sophisticated mathematical analysis. The central finding was that spacetime can bend further than earlier models assumed. Previous calculations had made certain assumptions about how the warp bubble geometry must blend into the surrounding universe. Assumptions based on mathematical convenience and computational tractability. When those assumptions were relaxed, the equations revealed a wider range of possible curvature profiles. Some of the newly identified profiles correspond to warp drives that use even less energy than the 2024 Fuchs design. A few might allow superluminal operation with significantly reduced exotic matter requirements. Reduced, not eliminated. But reduced enough that the problem might shift from impossible to merely extraordinarily difficult. The paper didn't claim to have solved the faster-than-light problem. What it claimed was that the solution space is larger than anyone had been exploring. For 30 years, warp drive research had been narrowing, eliminating candidate designs one by one as they failed energy conditions, stability tests, or other physical criteria. The new result argued that some of those eliminations were premature, that researchers had been searching a subset of the actual solution space, and that reopening the discarded regions might yield hybrid designs, combining the best features of multiple approaches. Research groups at universities in Germany, Australia, Japan, and the United Kingdom immediately began running simulations, using Warp Factory and other numerical tools to evaluate the newly identified metric families, checking which ones satisfy energy conditions, which ones are stable against small perturbations, which ones could plausibly be built with materials that might exist even if we don't have them yet. The work is ongoing. As of this recording, no paper has delivered a superluminal warp drive that passes every test and uses only ordinary matter. The superluminal barrier remains. But what has changed, subtly but significantly, is the attitude of the broader physics community. Throughout the 1990s and 2000s, warp drive research was fringe, tolerated in the literature because the math was valid but not taken seriously as a path to real technology. Conferences didn't feature sessions on it. Graduate students didn't write dissertations on it without raised eyebrows from their committees. Funding agencies didn't support it. By the mid-2020s, that changed. Papers on warp drive appear regularly in Classical and Quantum Gravity, Physical Review D, and other top-tier journals. Conference sessions on advanced propulsion draw large audiences. NASA maintains an interest, even if Eagle Works is no longer as active as it was. Private organizations like Applied Physics publish openly and collaborate with academic researchers. Graduate students cite warp metrics in their work without professional stigma. The field has moved from mathematical curiosity to legitimate engineering problem. The engineering might still be centuries away, but it's engineering, not fantasy. And that distinction matters. There is, however, one aspect of superluminal warp drive that needs to be addressed. The reason faster-than-light remains so difficult has everything to do with what happens at the front edge of the bubble when it crosses the light barrier. When a warp bubble moves faster than light, it creates something called a horizon. A horizon is a boundary in space-time, beyond which information cannot pass in certain directions. The most familiar example is a black hole event horizon. At a black hole's event horizon, space-time is falling inward, faster than light can propagate outward. Anything crossing that boundary cannot escape. not because it's being pulled by some overwhelming force, but because the geometry of space-time itself has changed such that all future directed paths point inward. There's no direction you can move that leads back out. A superluminal warp bubble generates a similar structure at its leading edge. The front wall of the bubble is moving outward faster than light, which means any signal sent from inside the bubble toward the front edge can never catch up. The front edge is receding faster than the signal can propagate. This creates a causal disconnect. The ship's interior is cut off from its own leading edge. A radio signal sent from the pilot's seat toward the front of the bubble would never arrive. The signal would chase the front wall forever, never catching up, never influencing what happens there. From a navigation standpoint, this is catastrophic. During the voyage, the ship cannot steer. It cannot adjust course. It cannot transmit any information ahead of its position. The bubble must be aimed correctly before launch, because once it's moving at superluminal speed, the crew has no causal access to the region of space they're heading toward. Any error in the initial trajectory cannot be corrected mid-flight. Any obstacle in the path cannot be avoided. The ship simply plows forward on whatever vector it was set to, unable to respond to changing conditions. It gets worse. A superluminal warp bubble also cannot be stopped from inside. To decelerate, the bubble would need to change its own geometry. Shift the distribution of matter or energy in the warping region. But doing that requires sending signals from the ship's interior to the bubble boundary. And if the bubble is moving faster than light, those signals cannot reach the leading edge. You're locked in. The only way to stop is to have external infrastructure at the destination. Pre-positioned equipment, set up by an earlier mission that can collapse the bubble from outside, or some kind of autonomous mechanism embedded in the bubble wall itself, programmed to shut down after a certain duration. Neither option is reassuring. The pilot, sitting in the control seat, has effectively become a passenger, watching the universe blur past through windows that no longer obey normal causality. Some theorists have proposed workarounds. One idea involves oscillating the bubble, switching it on and off at high frequency so the ship has brief moments of causal contact with the outside universe between warp pulses. The math for this exists in certain models, but it introduces severe stability problems. A bubble that keeps collapsing and reforming might emit catastrophic bursts of radiation with each cycle. The energy released could be enough to vaporize the ship. Another idea is to simply accept the limitation and design missions around it. Warp drives become long-range ballistic devices. You aim them carefully, launch them, and hope they arrive where you pointed them. For pre-planned routes between established destinations, this might be workable. For exploration, it's essentially useless. The horizon problem doesn't prove warp drive is impossible. It proves that superluminal warp drive, if it works, would be a fundamentally different kind of vehicle than anyone imagined. Not a steerable starship that you pilot like an airplane. A ballistic projectile that you aim and fire, with no ability to change course once launched. And there's a second consequence of the horizon that's even more dangerous. A consequence involving radiation. In 1974, Stephen Hawking published a result that shocked the physics community. He proved that black holes emit radiation. Before Hawking's work, everyone assumed black holes were perfectly black. No light escapes. No heat radiates away. They're cold, dark, silent objects that only absorb and never emit. Hawking showed that quantum mechanics changes the picture. Near the event horizon of a black hole, virtual particle pairs constantly pop into existence from the vacuum. Normally, these pairs annihilate almost immediately and disappear. But near a horizon, something different happens. One particle of the pair can fall into the black hole while the other escapes. The escaping particle becomes real, carrying energy away. From the outside, it looks like the black hole is radiating. This is called Hawking radiation. The temperature of the radiation depends on the size of the black hole. Larger black holes emit cooler radiation. Smaller black holes emit hotter radiation. A black hole, the mass of our Sun, would have a Hawking temperature of about 60 nanokelvins. That's 60 billionths of a degree above absolute zero. Far too cold to detect against the cosmic microwave background. But a smaller black hole, say one the mass of a mountain, would radiate at higher temperatures. And a microscopic black hole would be incredibly hot. Now, apply this same physics to a superluminal warp bubble. The bubble's leading edge forms a horizon. Not exactly like a black hole horizon, but similar in the relevant ways. It's a boundary where causal structure changes, where future-directed paths cannot cross back. And wherever you have a horizon, Hawking radiation should appear. Near the front wall of a superluminal warp bubble, virtual particle pairs pop into existence. One particle falls forward into the region the bubble is moving into. The other particle falls backward into the ship's interior. From the crew's perspective, particles are raining in from the leading edge. A constant stream of radiation generated by the horizon geometry itself. The problem is that warp bubbles are small, much smaller than astrophysical black holes, and radiation temperature scales inversely with horizon size. Smaller horizon means hotter radiation. A superluminal warp bubble moving at, say, 10 times the speed of light would have an effective horizon radius on the order of feet or tens of feet. Theoretical calculations suggest the Hawking temperature of such a horizon could be thousands or even millions of kelvins. Hotter than the surface of the Sun. The crew inside the bubble wouldn't just feel warm. They'd be bathed in high-energy particles pouring inward from the front wall. X-rays, gamma rays, possibly even more energetic radiation. The intensity would be lethal within seconds. A paper published in 2009 by physicists at the University of Sydney worked through this calculation in detail. Their conclusion was stark. Any macroscopic superluminal warp bubble would generate Hawking radiation at the leading edge, intense enough to kill the crew almost instantly. The faster the bubble moves, the hotter the radiation becomes. There's no escape. No shielding would help, because the radiation is being generated inside the bubble, between the ship and the front wall. Putting shielding between the crew and the source would require disrupting the bubble geometry itself, which would collapse the warp drive. Are there ways around this? Possibly. If the bubble wall could be shaped very carefully, some of the radiation might be redirected. Focused away from the ship's interior, out through the sides or back of the bubble. Alcubierre himself has speculated that quantum gravity corrections, the still unknown physics that unifies general relativity with quantum mechanics, might modify Hawking radiation in ways that soften the effect. At the scales where quantum gravity becomes important, roughly the Planck length of 10 to the negative 35 meters, Space-time itself might behave differently than classical general relativity predicts. Those modifications could change how horizons emit radiation. But this is speculation. We don't have a theory of quantum gravity. We don't know whether it would help or make things worse. There's also the subluminal escape clause. If the warp bubble moves slower than light, no true horizon forms. And without a horizon, there's no Hawking radiation. This is yet another reason why the subluminal warp drives, like the Fuchs design, are more practical. They avoid the radiation problem entirely by staying below the threshold where horizons appear. The Hawking radiation issue remains one of the most serious objections to superluminal warp travel. It's not an engineering challenge that better materials or more energy could solve. It's built into the structure of space-time and quantum field theory. A faster-than-light bubble creates a horizon. A horizon emits radiation. The radiation kills the crew. Unless something about our understanding of physics changes, this might be an absolute barrier. There's one more hazard worth discussing. Something that happens during the voyage itself, involving the matter and the bubble encounters along the way. Interstellar space is not truly empty. It's thinly populated. Hydrogen atoms, about 1 per cubic centimeter on average. Helium atoms, much rarer. Occasional grains of cosmic dust. Stray electrons and ions. Cosmic rays, high-energy particles from distant supernovae. For a spacecraft moving at conventional speeds, this sparse medium is negligible. Voyager has been traveling through it for 50 years without issue. But for a warp bubble moving at hundreds or thousands of times the speed of light, this thin gas becomes a problem. The physics was worked out in a 2012 paper by Brendan McMonagle, Geraint Lewis, and Philip O'Byrne. The team asked, what happens to the interstellar medium when a superluminal warp bubble plows through it? The answer was alarming. As the bubble moves forward, hydrogen atoms and dust particles in its path don't pass cleanly through the bubble. They get caught, trapped in the warped geometry at the leading edge. The compression of space-time accelerates these particles to enormous energies. They accumulate, building up a reservoir of matter traveling with the bubble. The longer the voyage, the more matter accumulates. A trip of several light years would sweep up billions upon billions of particles, each one carrying energy proportional to the bubble's velocity. When the bubble finally arrives at its destination and shuts down, all that accumulated matter gets released. The trapped particles blast outward from the ship's position in a tightly focused beam. The beam travels in the direction the ship was heading, directly toward the destination. The energy in this beam, according to McMonagle and colleagues, could be equivalent to hundreds of thousands of solar masses worth of kinetic energy, concentrated into a narrow cone. Anything in that cone would be annihilated. A warp ship arriving at Proxima Centauri wouldn't land gracefully. It would sterilize the star system. Any planets in the beam's path would have their atmospheres stripped away, their surfaces scorched down to bedrock, possibly vaporized entirely if the beam was intense enough. The ship itself would survive. It was inside the bubble, shielded from the release. But the civilization that sent it would have just committed an act of interstellar destruction, even if unintentionally. This is sometimes called the warp drive genocide problem, and it's not hypothetical. The math is straightforward. The effect scales with distance traveled and particle density encountered. Even the extremely low density of the interstellar medium, accumulated over light years, produces a devastating result. Some proposed solutions involve modifying the bubble geometry to deflect particles rather than trap them. A hydrodynamic shaping of the front wall that guides incoming matter around the sides of the bubble. Other proposals suggest ending the voyage far from the destination, in empty space, and letting the beam disperse harmlessly before approaching under conventional propulsion. Both ideas add complexity. Both introduce new potential failure modes. For mission planners, the particle accumulation problem means superluminal warp ships couldn't approach inhabited star systems directly. They'd need arrival protocols, long deceleration zones, careful alignment to aim the exit beam away from anything valuable, advance warning to civilizations at the destination, assuming they exist and have the technology to receive messages. It's yet another complication, stacked on top of the exotic matter requirement, the horizon problem, the Hawking radiation, and the steering limitations. Between all of these issues, the original Alcubierre warp drive started looking less like a sleek starship and more like an uncontrollable weapon that happens to transport cargo. Which raises a question. If warp drive has all these problems, is there a different approach to faster-than-light travel that avoids them? There is. Sort of. Instead of warping space around a ship, imagine cutting a tunnel directly through space itself. A shortcut. A path connecting two distant points along a route shorter than the surrounding universe allows. The ship doesn't need to move fast at all. It walks through the tunnel, emerges light years away moments later. This is called a wormhole. And like warp drive, wormholes emerge from Einstein's equations as mathematically valid solutions. The basic concept was first described by Albert Einstein and Nathan Rosen in 1935. They were studying the interior geometry of black holes and discovered that the mathematics permitted a bridge, a connection between two otherwise separate regions of spacetime. The Einstein-Rosen bridge, as it became known, was a feature of the Schwarzschild black hole solution. It linked the black hole's interior to another region, possibly another universe entirely, or a distant part of our own universe. Early physicists treated this as mathematical curiosity. The bridge wasn't traversable. It would collapse too quickly for anything to pass through. And even if you could enter it, you'd be crushed by tidal forces before reaching the other side. The situation changed in 1988. Kip Thorne, a theoretical physicist at Caltech who would later win the Nobel Prize for the first detection of gravitational waves, published a paper with collaborators Michael Morris and Ulvi Yurtseva. The title was Wormholes in Spacetime and Their Use for Interstellar Travel. The paper was partly inspired by a request from Carl Sagan. Sagan was writing the science fiction novel Contact and wanted a scientifically plausible way for his characters to travel faster than light. He asked Thorne if there was any mechanism permitted by general relativity. Thorne took the question seriously. His team's result was striking. Traversable wormholes, meaning wormholes you could actually travel through without being destroyed, were valid solutions to Einstein's equations, provided certain conditions were met. A spacecraft could enter one mouth of the wormhole, travel through a short throat connecting the mouths, and emerge from the exit potentially light years away. The journey through the throat could take minutes or hours. The two mouths could be separated by any distance, across the galaxy if you wanted. From the outside, the trip would appear instantaneous, or nearly so. The ship disappears into one mouth, reappears from the other, potentially before any light signal following the normal route could make the journey. Think of space-time as a sheet of paper. Normally, to get from one point to another, you travel across the surface. A wormhole is like folding the paper so the 2 points touch, then poking a hole through both layers. The hole creates a shortcut. The distance through the hole is much shorter than the distance across the surface. The trip through the wormhole doesn't exceed light speed locally. A photon racing through would still move at 300,000 kilometers per second through the throat. But the shortcut makes the effective travel time much less than going the long way around. An observer, watching from outside, would see a ship enter one mouth and emerge from the other almost instantly. Potentially faster than light could have made the trip through normal space. Unlike warp drive, wormholes don't involve moving through space at all. There's no bubble racing across the universe. No compression or expansion of the surrounding geometry. The tunnel exists as a fixed structure, a permanent feature of space-time with entry and exit points that don't move. The ship simply flies through. In principle, you could position the mouths anywhere in the universe. One mouth in Earth orbit, the other in orbit around a planet at Alpha Centauri. Step through one, emerge from the other. The engineering problems, however, make warp drive look simple by comparison. Kip Thorne's 1988 paper laid out the requirements for a traversable wormhole. The list is demanding. First, the wormhole must have no event horizon. An event horizon is a one-way boundary. Cross it and you can't come back. If a wormhole had an event horizon, travelers entering would be trapped. Most naturally occurring wormhole solutions, including the Einstein-Rosen bridge, have horizons. They're not traversable. A usable wormhole requires specific geometry where both mouths are open, accessible, and connected with no barriers. Second, the throat must be wide enough for a spacecraft. Obvious, but important. In a narrow throat, tidal forces would be extreme. The difference in gravitational pull between the nose and tail of a ship could stretch the vehicle apart. Thorne calculated that for a human-scale spacecraft to transit safely, the throat needs a minimum radius of several miles. Anything smaller, and the tidal stresses would destroy the ship. Third, the transit time must be reasonable. A wormhole where time passes much faster or slower inside than outside is problematic. Thorne showed that throats with ordinary local time flow are possible if the matter holding the wormhole open is arranged correctly. Fourth, and most critical, the wormhole must be held open. This is where the physics becomes impossible with current knowledge. Ordinary matter, the kind that makes up stars, planets, and everything we interact with, curves space-time inward. Gravity is attractive. It pulls. A wormhole throat, being a tunnel through space-time, naturally wants to pinch shut under this attractive force. It's unstable. To keep it open, you need something that pushes outward, something that creates repulsive gravity. Thorne identified what's required. Exotic matter. Matter with negative energy density. The exact same substance Alcubierre's warp drive needs. The stuff that might not exist. And for a wormhole, you need a lot of it. Thorne estimated that holding open a wormhole large enough for a mile-scale spacecraft would require exotic matter comparable to the mass of a large planet, arranged in a shell around the throat. in a precise, geometric configuration. The setup is delicate. Any fluctuation in the exotic matter distribution could cause the throat to collapse. And if the throat collapses while a ship is inside, the ship is crushed out of existence. Compare this to warp drive. A warp bubble needs exotic matter in a shell around the ship. The shell is moving through space. Once it's configured and accelerated, it just maintains its shape. Modern designs like the Fuchs solution have eliminated the exotic matter requirement entirely for subluminal cases. A wormhole is fundamentally different. The exotic matter isn't decorative. It's structural. It's holding the wormhole throat open against constant gravitational pressure. Remove the exotic matter for even a microsecond, and the throat collapses. The quantity required is also larger. Thorne's planet mass estimate applies to a relatively modest wormhole. Scaling up to larger apertures or longer connections increases the requirement. Some calculations suggest a wormhole suitable for regular interstellar traffic would require exotic matter equivalent to several stars' worth of mass, all concentrated in the throat region. If ordinary matter were packed that densely, it would collapse into a black hole. Exotic matter, by definition, behaves differently. But the geometric demands are severe regardless. There's also a stability problem. Researchers have analyzed perturbations to wormhole geometries. Small disturbances, tiny fluctuations in the exotic matter distribution. Most configurations are unstable. A perturbation causes the throat to start collapsing. Once collapse begins, it proceeds catastrophically. The wormhole pinches shut in a fraction of a second. Anything inside is destroyed. Making a wormhole stable requires incredibly precise balance. Conditions that may not be physically achievable. Compare this to Subluminal warp drive, where the applied physics team demonstrated a design using only positive energy. No analogous result exists for wormholes. Every traversable wormhole solution anyone has written down requires exotic matter in the throat. The no-go theorems in this area are stronger than for warp drive. While subluminal warp might be possible with known physics, wormholes appear to require genuinely new physics. A breakthrough we haven't made. For mission planners comparing the two approaches, the choice is clear. Warp drive, at least in subluminal form, connects to existing physics and plausible future materials science. Wormholes require a fundamental advance in our understanding of matter and energy. Both are faster than light concepts, at least in principle. Only one has a visible path forward. But there is one place in the universe where negative energy has been confirmed to exist. And it might be the key to understanding whether either technology could ever be real. In 1948, a Dutch physicist named Hendrik Casimir was working at the Philips Research Laboratory in Eindhoven, Netherlands. He was studying the quantum behavior of electromagnetic fields. And he predicted something strange. Two uncharged parallel metal plates, placed very close together in a vacuum, should attract each other. Not because of gravity, which is far too weak at such small scales. Not because of static electricity, since the plates are neutral. The attraction, Casimir said, would come from the quantum vacuum itself. His prediction was based on quantum field theory. The theory says that empty space isn't truly empty. It seethes with activity. Virtual particles constantly pop into existence in pairs, exist for a tiny fraction of a second, and annihilate. These fluctuations happen everywhere, at all times, for all types of fields. Electromagnetic fields fluctuate. Virtual photons appear and disappear. When you place two metal plates close together, you impose boundary conditions on these fluctuations. Certain electromagnetic wavelengths can't fit between the plates. The wavelengths are longer than the gap, so those modes are suppressed, excluded from the space between the plates. But they continue to exist in the space outside the plates. This creates an imbalance. More virtual photons pressing on the outside than on the inside. The net result is a force pushing the plates together. This is the Casimir effect. It sounds like science fiction, but it's real. It was first measured experimentally in 1997 by Steve Lamoureux at Los Alamos National Laboratory. He used metal plates, separated by gaps of about 1 micrometer, 1,000th of a millimeter, and he detected the attraction. Since then, the effect has been measured in multiple laboratories with increasing precision. Modern experiments can detect Casimir forces with exquisite sensitivity. What matters for warp drive and wormhole research is this. The region between Casimir plates has a lower energy density than the vacuum outside, lower than ordinary empty space, which means, by definition, it has negative energy density relative to the baseline. It's the only confirmed example in all of physics of a place where genuine negative energy exists in bulk, not virtual particles that exist for infinitesimal times. Actual, measurable, persistent, negative energy. The Casimir effect proves that negative energy is not forbidden by nature, at least not in small amounts, at least not under specific conditions. The question is whether it can be scaled up. Can you produce enough negative energy to power a warp drive or hold open a wormhole? The answer, with current technology, is unambiguously no. The amount of negative energy in a Casimir cavity is tiny. A pair of plates, 1 square meter in area, separated by a gap of 1 micrometer, produces total negative energy on the order of 10 to the negative 7th joules. 1/10,000,000th of a joule. That's less energy than it takes a mosquito to flap its wings once. For comparison, warp drive designs call for negative energy measured in kilograms or tons of mass equivalent. Using Einstein's equation, E equals mc squared, 1 kilogram of mass corresponds to about 9 times 10 to the 17th joules of energy. The gap between what a Casimir cavity produces and what a warp drive needs is about 24 orders of magnitude, a factor of 1 trillion. Nevertheless, the Casimir effect is cited in every serious warp drive paper because it proves the concept. Negative energy can exist. It exists in laboratories right now, between carefully prepared metal surfaces. The question of whether we can scale it up is a question of engineering. Extraordinarily difficult engineering. But engineering, not fundamental physics saying no. Several speculative proposals have been floated over the years, each attempting to find a way around the scaling problem. One idea involves stacking many Casimir cavities, thousands or millions of them. Each individual cavity contributes a tiny amount of negative energy. The hope is that if you build enough of them and arrange them properly, the contributions add up. 10,000 cavities, producing 10,000 times the effect of one. 1,000,000 cavities, producing 1,000,000 times more. Scale it up far enough, and maybe you reach the levels warp drive requires. The problem is that cavities interfere with each other in complex ways. The electromagnetic modes, suppressed in one cavity, affect the boundary conditions in neighboring cavities. The vacuum fluctuations aren't independent. They're coupled through the geometry. The result is that the gains don't add linearly. Stacking 10,000 cavities doesn't give you 10,000 times the effect. It gives you something much less. The interference effects become dominant as you try to scale up, and the net benefit diminishes rapidly. Researchers have tried various geometric arrangements to minimize the interference. Different spacing patterns, different plate materials, different cavity shapes. Nothing has produced a breakthrough. Another idea involves dynamic Casimir effects. If you move the plates rapidly, oscillating them back and forth at very high frequency, you can do something interesting. The moving boundary conditions don't just suppress vacuum modes. They convert virtual photons into real ones. The oscillating plates shake the quantum vacuum hard enough that some of the fluctuations become actual particles. Photons that escape the cavity and carry energy away. This has been demonstrated experimentally. In 2011, researchers at Chalmers University in Sweden built a device that exhibited the dynamic Casimir effect. They used a superconducting circuit that mimicked a moving mirror, and they detected real photons emerging from the vacuum. It was a landmark result. Proof that the quantum vacuum can be manipulated to produce real particles and real energy. But the amount of energy produced was even smaller than the static Casimir effect. The photons were faint. The power output measured in unimaginably tiny fractions of a watt. Scaling this up to warp drive levels would require oscillating massive structures at frequencies that would tear them apart. The materials don't exist that could survive the forces involved. A third idea looks at other quantum fields beyond electromagnetism. The Casimir effect we've been discussing works for the electromagnetic field. Virtual photons between metal plates. But nature has other fields. The electron field, which fills all of space and whose excitations are the electrons we know. Quark fields, whose excitations are the quarks that make up protons and neutrons. The Higgs field, whose excitations are Higgs bosons and which gives particles their mass. Each of these fields has its own vacuum structure, its own fluctuations, its own potential for producing Casimir-like effects. Maybe one of them produces stronger negative energy when confined between boundaries. Maybe some combination of fields produces effects that reinforce rather than interfere. Researchers have explored these possibilities theoretically, calculating what would happen if you could impose boundary conditions on electron fields or quark fields the way you impose them on electromagnetic fields with metal plates. The math is complicated. Quantum field theory at this level involves calculations that push even modern supercomputers to their limits. But so far, nobody has found a field configuration that produces dramatically more negative energy than the electromagnetic Casimir effect. The numbers remain stubbornly small. There's also a theoretical constraint that makes scaling difficult. Something called the quantum inequalities, proven by physicists Larry Ford and Thomas Roman in the 1990s. These are mathematical theorems showing that negative energy, when it exists, comes with strict limitations. The more intense the negative energy, the shorter the time it can persist, and the smaller the volume it can occupy. It's a cosmic trade-off built into quantum field theory. You can have a lot of negative energy, but only for an instant and in a tiny region. Or you can have a little negative energy sustained over a longer time in a larger volume. But you can't have large amounts sustained indefinitely in a macroscopic region, which is exactly what a warp drive would need. The quantum inequalities don't absolutely forbid warp drives, but they make them extraordinarily difficult to build using negative energy extracted from quantum vacuum fluctuations. You'd need to find a loophole, a configuration where the inequalities don't apply or where they're less restrictive. Such loopholes might exist. Quantum gravity, the still unknown theory that unifies general relativity with quantum mechanics, might modify the inequalities in important ways. Or new physics, beyond the standard model, might reveal fields or particles with properties that circumvent the constraints. But these are speculations. We don't have quantum gravity yet. We haven't found any physics beyond the standard model that helps with negative energy production. The engineering remains aspirational. All of these approaches are active research areas. Small teams at universities and national labs working on the problem, making incremental progress, measuring smaller forces, understanding the physics more deeply. But none of them has produced a practical reservoir of negative energy at the scales warp drive or wormholes would require. The engineering challenge is immense. It might remain immense forever, or it might yield to some future insight we can't predict. Which means that on the longest possible timescale, warp drive might not require entirely new physics. It might just require extraordinarily patient refinement of the physics we already have. But there's one more piece of this puzzle worth exploring. If warp drives exist anywhere in the universe, and if they occasionally fail, we might be able to detect them. In 2024, Katie Clough and collaborators at Queen Mary University of London published a paper in Classical and Quantum Gravity. The title was "What No One Has Seen Before: Gravitational Waveforms from Warp Drive Collapse." The paper asked a question nobody had seriously addressed before. What happens when a warp bubble fails? Not how it might fail, but what observable signature the failure would leave. The setup is straightforward. A warp bubble is a structured region of spacetime held together by a specific distribution of matter and energy. If that distribution becomes unstable, the bubble collapses. And the collapse isn't gentle. It's rapid, violent, catastrophic. The curved spacetime geometry suddenly relaxes back to flat. All the energy that was stored in the curvature gets released. Clough's team used numerical relativity simulations to model this. Numerical relativity is a branch of computational physics that solves Einstein's equations on supercomputers. It's the same technique used to simulate black hole mergers and neutron star collisions, the events that LIGO detects. Clough's group set up a warp bubble metric in their simulation. They gave it a physically reasonable matter distribution. Then they perturbed it, introduced a small instability, and let the simulation run. The bubble collapsed. And as it collapsed, it emitted gravitational waves, ripples in spacetime, propagating outward at the speed of light. The waveform had a specific shape, a brief burst of high-frequency oscillations. followed by a ring down, a decaying sinusoidal pattern as the geometry settled. The overall signature was distinct from any known astrophysical source, different from the chirp of merging black holes, different from the quieter signal of colliding neutron stars, different from supernova core collapse or any other violent event we know about. This matters because if warp drives exist anywhere in the universe, and if they sometimes break, those failures would send out gravitational waves. Waves that travel across the cosmos at light speed. Waves that, in principle, we could detect. The frequency of the signal depends on the size of the warp bubble. Clough's team calculated that for a bubble with a diameter of a few miles, the dominant frequency would be around 300 kHz, 300,000 cycles per second. That's much higher than the frequencies LIGO is designed to detect. LIGO operates in the range of 10 Hz to a few kilohertz. Its sensitivity peaks around 100 Hz. A warp drive collapse signal at 300 kHz would be completely outside LIGO's detection band. Even if one happened in our own galaxy, LIGO wouldn't hear it. But future detectors could. There are proposals for high-frequency gravitational wave observatories, instruments using different technologies than LIGO. Some involve superconducting resonators. Others use levitated sensors. Others use microwave cavity arrays. These designs are still in development. None has been built at the scale needed to detect astrophysical sources. But if they achieve their projected sensitivity, they would open a new window on the gravitational wave sky. And warp drive collapses would be a candidate signal. There's a speculative but tantalizing implication. The search for extraterrestrial intelligence has traditionally focused on electromagnetic signals, radio telescopes scanning the sky for artificial transmissions, optical telescopes looking for laser pulses, infrared surveys searching for waste heat from megastructures. All of these assume alien civilizations use or leak electromagnetic radiation we can detect. Gravitational waves offer a different channel. If an advanced civilization operates warp drives, and if those drives occasionally fail, the gravitational wave signatures would propagate outward, eventually reaching Earth. By searching for the specific waveforms predicted by warp bubble collapse, astronomers could potentially detect not just the existence of alien civilizations, but evidence of their advanced technology. This is admittedly a long shot. The probability chain has many weak links. Advanced civilizations must exist. They must use warp drives. Their drives must fail often enough to produce detectable signals. We must have instruments sensitive enough to catch those signals. And we must be looking in the right place at the right time. Each of those conditions is uncertain. Multiply the uncertainties together, and the result is a small number. But it's not zero. And the possibility has given gravitational wave astronomers a new target, a new template to add to their search algorithms. Even if nothing is ever found, a thorough search places constraints, limits on how common warp-capable civilizations are in our cosmic neighborhood. The work also has immediate scientific value beyond the search for aliens. By modeling warp bubble collapse in numerical relativity, Clough's team developed techniques for simulating exotic spacetimes, geometries that violate the classical energy conditions. These techniques are useful for studying other problems in general relativity. Black hole interiors. The Big Bang singularity. Hypothetical cosmic strings. The tools developed for one problem often find applications elsewhere, which means the hunt for faster-than-light travel, even if it never succeeds in its primary goal, produces scientific progress as a side effect. And that brings us to the final question. The honest question every mission planner, every physicist, every science enthusiast has to confront. Where does this actually leave us? The question at the beginning was whether humanity has found a real way to travel faster than light. After everything we've covered, the answer needs to be honest about what's possible, what's not, and where the boundary lies. What the mathematics says yes to is significant. Warp drive, as a solution to Einstein's field equations, is valid. It has been since Miguel Alcubierre proved it in 1994. 3 decades of subsequent research have refined it, optimized it, explored its limits. But the core concept has never been invalidated. Warp spacetimes are real solutions to real equations describing how gravity and spacetime behave. What the mathematics also says yes to, based on the applied physics work of the last 5 years, is that warp drive does not necessarily require exotic matter, at least not for subluminal designs. The Fuchs 2024 paper demonstrated a warp bubble using only ordinary positive energy, satisfying all the classical energy conditions, built from matter that exists in nature. This is a genuine result, published in a respected peer-reviewed journal, reviewed by experts who found no errors in the analysis. It moves warp drive from pure theory into the realm of plausible engineering. Not engineering we can do today. Not engineering we can do this century. But engineering that's consistent with known physics. What the mathematics still says no to is faster-than-light travel without exotic matter. Every superluminal warp drive configuration identified so far violates at least one energy condition, requires at least some amount of negative energy. No-go theorems, while not absolute proofs, make most physicists skeptical that this will change. The light barrier might hold for warp drives just as firmly as it holds for rockets, just for subtler reasons. What the mathematics is ambiguous about is everything in between. Whether Casimir effects or other quantum processes can be scaled up to produce usable amounts of negative energy. Whether new physics beyond the standard model might provide loopholes. Whether mathematical approaches not yet discovered will reveal solutions we haven't found. These are open questions. They might stay open for decades, or centuries, or forever. The gap between theory and practice is closing in one sense. We understand the problem much better than we did in 1994. The Alcubierre paper treated warp drive as a curiosity, a fun exercise in solving Einstein's equations. The Bobrick-Martyr framework treats it as a systematic engineering challenge. Warp Factory lets researchers evaluate designs numerically, run simulations, test stability, map the solution space methodically. Numerical relativity lets teams model what happens when things go wrong. Gravitational wave observatories might soon search for signatures of alien warp technology. All of this is real progress, real tools, real research programs, real papers being published and cited. But the gap between theory and practice is not closing in the sense of being near a working vehicle. The energy requirements for even subluminal warp drives remain beyond anything our civilization can produce. We're talking power outputs comparable to significant fractions of total global electricity generation, sustained for hours or days, focused into a matter shell that has to maintain its shape under stresses we can't currently handle. The materials science for building a stable warp shell doesn't exist. We need substances that can handle pressures thousands of times higher than the best alloys we have. Materials that can maintain precise geometric configurations under extreme thermal and gravitational loads. We're centuries away from that capability. The instrumentation for testing even small-scale warp effects doesn't exist at the required precision. Before anyone builds a starship, someone has to demonstrate the effect works in a laboratory. Measure tiny amounts of spacetime curvature around benchtop experiments. We can detect gravitational waves from black holes colliding billions of light-years away. But measuring static local curvature from a small mass distribution is a completely different problem. One we haven't solved. For a mission planner writing an actual proposal, the assessment is clear. Warp drive is real as a physics concept. The equations permit it. Warp drive is plausible as a long-term engineering goal. There's a path, however distant, connecting current knowledge to eventual capability. Warp drive is not imminent as a technology. Not this decade. Not next decade. Almost certainly not this century. Probably not for several centuries. The interstellar voyages of science fiction, where starships hop between systems as casually as airplanes cross continents, remain fantasy. Ships crossing the galaxy in days. Crews visiting dozens of worlds in a single career. That's still fiction. But fantasy is not the same as impossibility. The difference matters. A fantasy has no path to reality. It violates fundamental laws. It requires magic or suspension of disbelief. A long-term engineering goal, by contrast, is consistent with known physics. Hard, yes. Expensive, yes. Centuries away, yes. But not forbidden. Warp drive clears that bar. It clears it by a narrow margin. It clears it with caveats and conditions. But it clears it. The research community continues building on that foundation. Papers appear every year. New designs are proposed and analyzed. Old designs are refined. The solution space expands slowly. Humanity may never leave the solar system with warp drive. Our civilization might collapse before we develop the technology. Or we might find that some deeper law of physics we haven't discovered yet forbids it after all. But the alternative is also possible. On some distant century, a research team might crack the final problems. Build the first test bubble. Demonstrate that it works. Scale it up. And humanity lights up a warp drive for the first time. Crosses to Proxima Centauri, not in 70,000 years, but in years. Reaches Sirius. Reaches Vega. Spreads across the local stellar neighborhood. The mathematics says this outcome is not forbidden. The engineering says it's not close. The honest verdict is patience. The honest strategy is to keep working. One equation at a time. One experiment at a time. One refinement at a time. Because the distance to Proxima Centauri is 25 trillion miles. And a species that walked on the Moon, landed rovers on Mars, detected gravitational waves from merging black holes billions of light years away, and photographed the event horizon of a supermassive black hole at the center of a distant galaxy. Doesn't give up on a problem just because the numbers look hard. The mission brief ends here. The equations are written. The simulations are running. The instruments are being designed. And somewhere, in a future we can't quite see yet, the first warp bubble might be learning how to bend space itself.